called strong sub-additivity. Sub-additive. Okay, so now I'm going to consider two overlapping regions. So this is A and this is B, but they are overlapping here. So this is the intersection of A and B. In this case, the entanglement entropy, so the sum of the entanglement entropy or the region of the union of A and B plus the entropy of in the union plus the intersection is less than the sum of each regions. So here I have the union A and B, and here I have the intersection of A and B, and the sum of these two terms are less than the right hand side. So this is very very important property, and this follows from the unitarity. So unitarity of the Hilbert space. Unitarity. So the proof is based on the harmicity of the density matrix, and I will use this relation in my later talks. And another interesting quantity other than the entanglement entropy is called mutual information. Mutual information. So mutual information needs two regions, A and B, but they are disjoint. So here's my A and here's my B, but they are disjoint. In this case, so you define the mutual information as the sum of the entropy for A plus entropy for B minus the entropy for the union. And by using this strong subjectivity, then you see that the mutual information is always positive, because now the intersection of A and B are just empty. If the intersection is empty, so you don't have any term here. So this inequality guarantees that the mutual information is positive. And in addition, this is very nice because it is always finite. So finite means that the entanglement entropy itself has UV divergences. It needs some renormalization. I mean, once you introduce the UV cutoff in your theory, in quantum field theory, then it is divergent. I mean, if you have UV cutoff epsilon, then in D dimension, if you have D dimension quantum field theory, then S of A has UV divergence e to the d minus 2, and whose coefficient is proportional to the area of the boundary of the region A. So I will talk about it later. So in this sense, the entanglement entropy itself has UV divergence, but the mutual information doesn't have any epsilon dependence. So UV divergence is cancelled inside this definition. So in this sense, this is better quantity.
Sorry, so here you're thinking of some local theory on the space, and A and B refer to a subset of the space?
Yes, these are regions.
Okay.
So this is my spatial slice in quantum field theory.
And part of the boundary belongs to A, up to your
Part of I always consider the closed system. I mean, I don't have any open boundary. I have closed system.
The finiteness of I follows from this definition, or you need some more things?
Okay, so the leading term apparently cancels because here I have two regions. The leading
Yes.
term is proportional to the area. So in this combination, so you don't see any divergence. But the cancellation in the subleading terms are non-trivial.
If I just do the measurement of entanglement entropy in region A without knowing anything about region B, do I know whether A and B are entangled?
Why? So which example are you talking about here?
Yeah. So if I just measure S sub A without knowing anything about the region, what's happening in region B, do I know whether A and B are entangled?
Okay, so in this example, okay, so I mean, here I have a system. I divide my system into two pieces,
Right.
A and its complement,
Right.
and complement is B.
Right.
Okay, so they are kind of entangled. But it depends on your ground state vector. If you consider the entangled state, then you can measure the entanglement by computing the entanglement entropy.
But if I can measure or compute entanglement in region A, entanglement entropy, do I know whether A and B are entangled?
If we measure the non-trivial entanglement entropy, then they are entangled.
Then we do know whether A and B are entangled, right?
Yeah.
So the question is, if we measure the entanglement entropy in our universe, can we know whether our universe is entangled with something else?
Yes, yeah, you can think of it because okay, so given the region A, and if you somehow compute the entanglement entropy for the region A by using only the information inside region A, then so I think you can somehow, let's say, yeah, you can regard your system as a submanifold, subregion of the larger space, and A and its complement are entangled somehow.
Do you expect our universe is entangled with something else?
Yeah, formally I think you can regard it like that. Yeah, so I think there is some trick to extend your Hilbert state from the region A to the whole system.
So can we say that if we can measure the entanglement entropy of our universe, somehow this could check the idea of multiverse?
I'm not sure. I'm not sure it works, but yeah, very formally, yeah, given any system, say the region A, and if you have non-trivial entanglement, then you can extend your Hilbert space to the larger space where the region A is a subsystem of that. And you can regard the entanglement entropy for A as a entanglement between A and its complement.
So is entanglement entropy an observable? In the sense that is there an experiment that can measure entanglement?
There is an experimental proposal, but nobody has not measured it.
But in principle, is it observable?
I expect that it is observable, but it's not observed yet.
So what's the proposal for the actual experimental setup?
I don't understand fully, but there is a paper by honest metaphysicist. Yeah. If you want, yeah, I can tell you which paper it is in private.
Do you believe?
I'm not sure.
He will tell you, right?
Oh, I see.
You know, sometimes people say that the only things that are observables are measurements of commission operators. So is there some sort? I mean, it's not clear to me that entanglement entropy falls in that class.
It is kind of observable because it is Hermitian. So the definition of entropy is minus trace of rho A times log of rho A. And if you regard this part as an operator, you are taking the expectation value of this operator. And you can define a modular Hamiltonian, so by exponentiating some Hamiltonian. It is not the usual Hamiltonian, but it is called modular Hamiltonian. And modular Hamiltonian is Hermitian, because rho A is also Hermitian. I'm not sure my definition is correct, but anyway, yeah.
Excuse me, the dominant divergence is related to area. The non-dominant divergence are non-geometrical.
It is geometrical, yeah, geometrical, yeah.
But it is also given by the area.
It's not given by the area, but it is some integral over the boundary of region A. So some local integral over the boundaries. Okay, so I will introduce one more quantity, so which is the Renyi entropy. So the Renyi entropy is a one-parameter generalization of an entanglement entropy. So here I have an integer, for any integer, and it is positive. Then you can define Renyi entropy for the region A as follows. You have log of trace of row A to the n, and you divide it by 1 minus n. So I will denote it by Sn. And if you take n goes to 1 limit, then you can recover the entanglement entropy for the region A. You take a limit, n goes to 1. And in the original definition of the entanglement entropy, we had a log of row A, and but this one doesn't have any log, so it's suitable for practical computation. And here I assume that the analytic computation works here. Usually n is supposed to be an integer, but here I analytically continue n to any real values. Okay, then. Is there any questions so far? Okay, then I'm going to talk about the entanglement entropy in quantum field theories. Okay, so we have considered a quantum system with finite dimension, but in quantum field theory, the dimension of the Hilbert space is infinite. So it's hard to compute the entanglement entropy or the reduced entropy matrix because we don't know the orthonormal basis for your quantum field theory in general. So here I'd like to introduce a trick. It is called replica trick. So instead of computing the reduced entropy matrix for the region A, I will compute this part, trace of row A to the n, by using some path integral representation. So I will rewrite this part as a partial function on some space. So to rewrite this part in the path integral formulation, then I will denote the ground state vector as follows. So here I have a path integral. This is Euclidean path integral, and this is a spatial region X, and so you have a ground state vector. So you start with time minus infinity, and you let it evolve to t equal to 0. And here I have a boundary condition phi naught at t equal to 0. So here I have a boundary condition phi should be phi naught at t equal to 0. Okay, and similarly, the inner product between phi and the psi and the sine of theta is a path integral from t equal to 0 to t equal to infinity. So this is t equal to infinity, and this is t equal to 0. And I have a boundary condition. I have a boundary condition at t equal to 0. It is given by phi naught theta. Phi is equal to phi naught theta at t equal to 0. And since our density matrix for the total system is given by psi and psi, two vectors, so you can rewrite your reduced density matrix in path integral representation. So I'm going to evaluate the reduced density matrix with two indices, small a and small b. Because this is the matrix, it has two indices, a and b. So the meaning of a and b's are just some boundary condition, or you have a state phi a for the region a, and you have rho a. So this is the dimension. And here you have phi b a. You have two states, phi a and phi b, with small characters. But since this guy is pure, this is the reduced density matrix. So you have a total density matrix psi, and you have to sandwich this state by a state for b. But since we are working on quantum field theory, so this part becomes so the summation becomes a path integral. Summation becomes path integral over some state phi b, but this is defined at t equal to 0. And the domain of this guy is inside the region b. Okay, and I have some state phi b and psi and phi b, and I have this state phi a, so it's phi b for the region a. Okay, so this is nothing but the reduced density matrix in quantum field theory. So I will continue this equation. So what we get is that we have path integral for the state b, phi b, and whose domains inside the region b equal to 0. But here, so we have a vector. So we have a vector phi a for the region a times phi b for the region b. So previously we had some state phi naught, but I will choose phi naught as a tensor product of phi a times phi b. Okay, and similarly, so I will choose phi naught tilde. Maybe they are opposite in my notation. Or this is correct, okay. So phi naught tilde is chosen to be phi BA. So my notation is very complicated. So anyway, so here I choose that phi naught is given by this state. This is tensor product, and also phi naught tilde is given by this tensor product. So then, this part can be written in path integral formulation. So I have path integral from t equal to 0 to t equal to infinity. And similarly, I have path integral from t equal to minus infinity to t equal to 0. But I slightly separate them. So this is 0 plus and this is 0 minus. I have path integral. And to illustrate this path integral, so I consider the semi-infinite line as a region A. So the A is the right hand side and region B is the left hand side.
Excuse me, if I remember, in the anti-digital space, time is a periodic variable, not extended from minus infinity to plus infinity.
Yeah, in the global coordinate, yes.
So how do you define the t equal infinity and the t equal minus?
But if you go to the, say, for example, in Poincare coordinate, or yeah, this is Euclidean time.
Euclidean time.
Euclidean time.
So T theory is defined on the boundary of the anti-digital space, and time is Euclideanized.
Yeah, this is the Euclidean time in my path integral representation.
Okay.
Yeah. So since I have a region A in the right hand side, so I have a state or boundary condition phi AA here. Here I have boundary condition phi A. Here I have boundary condition phi small b for the region A. And the left hand side has a boundary condition phi b. Okay. But since I have a path integral over phi b here, so I can rewrite this figure in this way. So I remove this guy, and I connect these two boundaries. I have path integrate over this part. Okay. Then in the end, what you get is that you have a path integral over the shaded region with two boundary conditions. Okay. You have boundary condition phi A at t equal to 0, but slightly below 0, and you have a boundary condition for phi B at t equal to 0, slightly above 0. So this is the path integral representation of my reduced density matrix. Okay. Then now, so I'm going to compute the trace of rho A to the n. Then trace of rho A to the n is, so I had a z1 here, so this is just a normalization, z1 to the n. But here I have n copies of path integral, so I have, this is the first path integral. But here I have boundary condition phi 1a below and phi 2a above. And in the second seat, I have a boundary condition phi 2 because I'm taking a trace. Okay, so these two indices should be equal. So here above I have phi 2, below here I should have phi 2 because I'm constructing two indices in the reduced nature matrix. But above I have another boundary condition, phi 3, and so on. And you have n copies of these Riemann surface, sorry, some slice. Here I have boundary condition phi 1 above and above, and here I have another boundary condition phi n. Oh, by the way, so this is the time direction t, and this is the spatial direction. So you have n copies. And I will write this guy as a Gaussian function Zn divided by Z1 to the n. So this guy, so this is the Gaussian function on this singular manifold. Okay, so you have very complicated geometry. So you have so if you go around this point, so this is the boundary of the region A. So if you go around the boundary of region A n times, then you come back to the original point. So this is the covering space. So with singularity at the boundary of the region A. So I will call this geometry as a Mn. So Mn is a singular manifold. This is a manifold with singular surface. Singular surface at the boundary of A. And I will call this boundary of A as an entangling surface. This is called entangling surface. Entangling surface. So entangling surface is the boundary of the region A. Okay, entangling surface. So this is a Gaussian function on the Mn. This is a Gaussian function on Mn. And then in this picture, so you can, okay, then you see that the Renyi entropy is given by the Gaussian function Vn. The Renyi entropy is given by log of Zn minus n times log of Z1 divided by 1 minus n. Okay. So once you know the Gaussian function on the singular space, then you can immediately get the entanglement entropy. So the problem reduces to the computation of the Gaussian function on some space, some manifold, but which is complicated in general. But anyway, in quantum field theory, so once you know this guy, so you are done. Okay. And by taking the n goes to 1 limit, so you take n goes to 1 limit, and then you have entanglement entropy. So you add this